no matter what area of mechanical engineering you choose to be interested in and practice in, or go to graduate school with and do some research, uh, over your engineering career, the probability of your having to do something with analyzing a pump is very probable. This is a case where the material in thermodynamics really, in an awful lot of cases, bleeds into all aspects of mechanical engineering. Uh, because mechanical engineer is a problem solver who does more than just work on his or her little specialty areas. We're problem solvers, and in general, we're always faced with needing to uh, move a material, a liquid material, from point A to point B. It's very predictable. So let's get started looking at how you can characterize the performance of a real, honest to goodness pump. So this is entitled Pump Efficiency, and I'm going to work you through the definition of how we define pump efficiency, and how this is a generally accepted definition of the way pumps work. And I'm going to try to illustrate that to you. Well, let's refresh. What is a pump anyway? And here's a great picture of a very typical single stage centrifugal water pump, or a process pump that we use in the process industry, in manufacturing, in operations of vehicles, all type of ships, airplanes, all types of things. So this is centrifugal pump. And if you want to look at some more details, I've already created a video out of Chapter 4 where we talked about open systems, and I've tried to highlight how would you sketch a pump? Here's a little sketch of a pump. How would you sketch a pump, and how would you analyze a pump? I'm going to give you some more details in this video about further very valuable methods in analyzing a pump and determining the power required by a pump. So again, let's refresh our memories on a couple of things. How would you sketch a pump? Well, here's the way I sketch basically, I try to depict a centrifugal pump operation with sort of the circle with the flow coming into the eye, or the eye of the rotor, or impeller of the pump, and then a sort of a discharge area, state two. Nearly always we're dealing with pumps that are operating in a steady state, steady flow manner. You clearly see that a pump has one inlet and one outlet. That's pretty common, of course. And so m.1 equals m.2. We'll just call that m dot. Let's also remind ourselves to get consistent with the textbook and consistent with typical engineering computations, the relationship between little w for an open system compared to w dot for an open system. So recall that little w out equals w dot out divided by m dot of the pump. Now, w dot of a pump, as I've shown here, I'm showing my block arrow coming out, but I'm always careful to write on my sketch, w dot of the pump is less than 0, because everybody knows it takes power to drive a pump, to pump a liquid from point A to point B, to increase its pressure from P1 to P2. So that's an important thing to maintain my sanity in the class and maintain my sanity as an engineer. I always show my W dot going out, but depict it and write it out. W dot is less than 0. So little w is less than 0 as well. I'm going to go back to your textbook, and your textbook does a very nice job of deriving what the textbook calls reversible work for an open system. Reversible work for an open system. Now, think back in your class all the way back to Chapter 2, where we had closed systems. We had a piston and cylinder. That's not an open system, is it? That's a closed system. Do you remember how work was derived, like capital W, the work for a closed system? Can you remember in your head what that was all about, and what the result was? remember that for a closed system, the work, little w, capital W over M, was the integral of P d little v. The integral of P d v, where v is little v. Little w for a closed system, integral P dv. You kind of keep that in the back of your head. The result for an open system is going to be dramatically different, and that's really, really important. I have stamped this slide important because this is the source of great confusion and computational blunders for many students, including myself from time to time as a student. But once I got into graduate school, I quickly learned the difference between work, W dot over M dot, or W over M, those difference between an open system and a closed system. And so rather than deriving the work for an open system in all these slides, I want to go back and I want to depend on your textbook and your reviewing your textbook. And I just want to hit the key points in the derivation. So we're going to start with this. Wow, does this look familiar to you? Section 6.13.2. Does this look familiar to you? Where at all? Could you identify what this governing equation is all about? That's the first law of thermodynamics for an open system, steady state, steady flow, one inlet and one outlet. So that should jump out at you as what that is without anybody telling you. All right, well, but I'm going to write it down for completeness. We've got steady state, steady flow, one inlet, one outlet. It's an open system. Now, what we're going to do is we're going to strike out this kinetic energy term. And we're going to strike out this potential energy term. So imagine in your mind striking those out. Okay. Remind yourself that m dot 1 equals m dot 2 just equals m dot. Okay. And little w is w dot over m dot. And that's called the work for a control volume, work for an open system. Thus, section 613 being called work. That's little w. All right. And so I'm jumping down now, that almost like a miracle occurs, and I'm jumping down to equation 6.51b. I'm this left-hand side, w dot over m dot. Well, that's little w. So I've written that out for you on the slide. W out for a reversible process. So this is an expression. This is an expression. It's a formula, but it's a governing equation expression for the work done by an open system for a reversible process 1 to 2. And here it is, minus the integral of V dP. Notice here it says kinetic energy change, potential energy change, both equal 0. Minus the integral of V dP. This is so important, I'm going to blow that up on the next slide. Make it bigger on the next slide. So I have made your text box screenshot bigger. Okay. This work has to do with W rev, which is this term here. So I've written it out. W dot reversible divided by M dot equals little w, the reversible work for an open system, steady state, steady flow, one in, one out, equals minus the integral of V dP. Oh, that is different than a closed system. I'm not even going to say what the closed system was now. But do you see that that's different than a closed system? First, I've got a pesky minus sign. The integral, that's the same. But look at this. Look at this. This integral expression. That is different, isn't it? And how is it different? I'm not going to say. You have to say that to yourself in your head. But for this open system, this is the definition of little w. And the other kind of interesting factoid that we're not going to use much, we don't use this much, is that you can visualize the work, W dot over M dot, on a pressure-specific volume diagram for an open system by visualizing the area under the curve, except integrating versus the y. Okay, and so do you see that this pink area, so it's not exactly the area under the curve, it's the area to the side of the curve, okay? But that's the visualization of work out, okay? And of course, the negative sign, you're going here. So this is, right, so you're kind of going, if you cock your head around like that, going from 1 to 2, you're kind of integrating from right to left if you got your head bent around. So the minus sign is what takes care of that. That's what makes it positive. Okay, whew, but this is, so I marked this important because the textbook sort of sandwiches this in. And when I was in graduate school, man, we spent a lot of time deriving this relationship. So the textbook time and the amount of time spent on this fundamental was much more than what your textbook devotes to in chapter 6. So just be aware of that, especially if you're graduate school bound. So I'm going to repeat it again. Little w reversible for an open system is minus the integral of VDP. Now I'm going to remind you of something else. Now we're back to pumps. What's this video? This video is about pumps, analyzing pumps. Well, what do we know about pumps? What do we do with pumps? We're pumping liquids like water, like lube oil, like hydraulic fluid. Okay, so we model, and so for water, we're pumping either saturated liquids, like my circles, or compressed liquids. And so I've shown this on a TS diagram because for open systems, we're mostly working on TS diagrams now. We're kind of ditching the PV diagrams for open systems and going towards TS diagrams for open systems. All right, and so we're generally in this phase to the left of the TS diagram. That's compressed liquid, and that's why I've shown my little pump over here in the blue. So reminder, over in the blue, a compressed liquid like water is considered an incompressible liquid. Incompressible liquid. What does that mean? What does incompressible liquid mean? Down here, it says that V, the specific volume of the liquid, is constant, such that V1, little v1 equals little v2. That's incompressible, constant specific volume. And so how do you get the specific volume of a liquid? Well, it says right out of the textbook in chapter 3. Here's your screenshot of chapter 3. It says evaluate V for a compressed liquid as V sub F at the temperature of the fluid. And so I say it a little better down here than this equation 311 does. It says V at the inlet of your pump and exit of your pump, little v is equal to V sub F at the temperature of the liquid going into the pump. V equals V sub F at the pump liquid inlet temperature. That is a key thing to remember. That is something that you're going to use almost day in, day out as a practicing engineer. If you choose to work in the thermal, fluids, or heat transfer areas of mechanical engineering, which I highly recommend you think about doing. All right, this is important. So this was a whole slide devoted to how do I get the specific volume, right? And let me go back a slide. Why is he talking about the specific volume stuff? The reason I'm talking about the specific volume stuff is this expression for work. Wow, look, if this is constant, if this little v is constant, I can pull it out of the integral, and the integral's easy, isn't it? It's minus little v times P2 minus P1, or to get rid of the pesky minus sign, it's little v times P1 minus P2. That's why I talked about v being constant. Pull it out of the integral. Makes life incredibly easy. All right, back to our pump analysis. So we're trying to analyze pumps. And so let's imagine a pump that is reversible and also fully insulated. Let's call it 1 to 2I for right now, okay? And then we've got a pump that somehow there's something irreversible going on in that pump. You can imagine maybe some kind of friction between the rotor, the impeller, and the casing, maybe. More likely is some type of unrestrained expansion where during the pressure increase process, you've got your liquid pumped up to a really high level, but oops, you kind of lose ground somehow within the pump, okay? And you get some unrestrained expansion of the liquid. So the pressure drops back down. Ugh. That would be that's irreversible, unrestrained expansion. So which would you expect which would you expect to take more power to drive your reversible and fully insulated pump compared to an actual pump? Well, common sense. You've been through the turbine, you've been through the compressor, so you know what the answer is. It takes less power to drive an irreversible. It takes my my check's in the wrong spot, isn't it? You would expect my check needs to go over to the right. It takes less power to drive a reversible adiabatic pump than it does to drive an irreversible adiabatic pump. I think check means that we've applied Common Sense 101 to see that this dot right here corresponds to the reversible adiabatic situation. It's a negative number, but the actual process is more negative. So this is a way to think about W dot being a positive number, things like for a turbine, and then W dot being a negative number for things like a pump or a compressor. So hope that helps you visualize, use Common Sense 101 to be able to figure out pump efficiency, because you're seeing the drill now. This is copy and paste. You'd expect a pump efficiency to be a number less than 100%, less than 1.0. And so you can figure, before we go to the next slide, you figured out what pump efficiency is going to be. Pump efficiency is going to be that reversible work term that we just derived out of the textbook, that minus the integral of VDP. That's going to be this term, W reversible, divided by W actual. So I've been careful to not call it isentropic for some subtle reasons. But anyway, W reversible divided by W actual is the formal definition of isentropic pump efficiency. We always model our pumps as fully insulated. The casing of the pump is fully insulated. There's no heat transfer to deal with. And so this is called the isentropic pump efficiency. W reversible over W actual. And then, so thank goodness I have, notice here, I don't have my vapor dome, right? And why is that? It's because I'm to the left of the dome. I'm in the compressed liquid region. And so here's what my sketch looks like for my reversible pump. And I have, darn it, I have mislabeled my TS diagram again. Shame on me. Look, let me escape out. This is shameful. I need to go and move to I over there and to A there. Let's see if I can get back to my presentation now. Whew, okay, not shameful anymore. I've got my reversible pump going from 1 to 2I, and then I've got my irreversible pump going from 1 to 2A. Now, the textbook calls this just state 2. I feel so much more comfortable throughout my years, and I was taught this as an undergraduate, all the way through graduate school, calling this point, this actual pump outlet state, state 2A. So that's my recommendation, is what you work with too. And then this 2I, this would be the reversible pump. It's also insulated. And you've heard my drill. It's a typically, and I'm going to show you, I hope coming up is going to be a slide where I'm going to show you some real honest to goodness ways to visualize, to be given pump efficiency. So typically we're given pump efficiency, or we determine it from what's called a pump curve. We're able, as engineers, we can calculate this reversible work, this minus the integral of VDP, using that easy formula that I kind of talked about but didn't write down. Okay, so typically we either have or can get both of those, and so typically we are solving for W actual down here. So that's why I've rewritten my definition of pump efficiency in this way. But still, I still say you can figure this out without going to a formula sheet or going back to your book. You ought to be able to figure this out in your head, because we use it so many times over and over again. And you're going to be doing that for the rest of the semester, dealing with systems, open systems that involve pumps. This is what I was hoping I would see. Here's the example of essentially being given a pump efficiency for an actual pump. You're going to be taking your fluid mechanics class. Either you're taking it now or you're going to take it later. And this is called a pump curve. And without telling you all the important ins and outs, but you do see that, well, let's look at these various curves. Do you see these different diameters, 18, 19, 20, 21? That would be the size of the pump impeller that you might order for a specific casing of a pump. So there's those things. Very involved, but the x-axis is volumetric flow rate in gallons per minute. Okay. The y-axis is, let's say it says total head and feet, but that would be the developed pressure, P2 minus P1. You can think of it as a pressure rise. And you can see here that this pump curve will, depending on where you land on your pump curve, that's going to tell you what your pump efficiency is. So let's see. I see the pump goes 74, 79, 74, and then 50. And so if you were trying to maximize your pump efficiency to minimize the amount of power required to drive your pump, you would endeavor to get your operating point and or select your pump sizes somewhere in this area where you land on this maximum pump efficiency line, 79%. So that's an example of the real world. It's really this is really the way we solve these problems in the world. This is where I want to give you some detail. I'm going to step you through some details about. So there's your theory. You can kick out this video. You've got the theory, but I'd like to step you through, if you're willing to hang in there, basically some tips on how would you analyze a pump in this class and then moving on into engineering practice. So typically the substance to be pumped is going to be water. All right, so for power plant operations, many processes, very common processes around your house, you're pumping water. Okay, so you got it. All right, water. I got water. My pump is open system, steady state, steady flow, one inlet, one outlet. Got it. What are you typically given or know about your computation? Typically, you're given the mass flow rate. Typically, you're able to determine the pressure increase. Typically, you either have P1 and P2, or you're able to determine P2 minus P1, the pressure increase. Nearly all the time, the inlet state of your pump the inlet phase is either going to be a saturated vapor, in other words, water that's nearly boiling, or it's a compressed liquid, like tap water, like water, like river water. You're trying to pump river water up to water your lawn. Okay, that would be a compressed liquid. You also are typically given or can find pump efficiency. You are to determine two things. How much power is required to drive the pump? That is a simple question that's asked, common question that's asked, and I'm going to try to show you how to go through that set of computations to determine how do I determine the power, kilowatts, required to drive a pump. Another question that is commonly asked that you're going to need to know how to do in this thermodynamics class is determine the actual outlet enthalpy of the pump, H2 actual, H2A. In other words, what is the actual enthalpy coming out of that pump? And I'm going to show you how to do that as well. Of course, you'll start with a sketch and plan your work. We've got water, okay. And so step one in our analysis, we're going to determine V1 and H1. So I've got to know the temperature of my liquid water coming in. So you know the drill. Go to your temperature table, look up your temperature. V1 is simply going to be VF. You write down a number. In this case, you got to slip the number 3 decimal places over because of the units. You're good at that already. You're also going to write down the enthalpy. H1 is simply H sub F at T1. So if it's 32 degrees C, you just write those numbers down. That's step one. Step two, determine the reversible work, W reversible. That's W dot over M dot for the reversible pump. Now your pump is actual. Your pump is irreversible. But first thing is you're going to get W reversible, okay? Let's go back to the fundamental. Let's write down the fundamental. W reversible is minus the integral of v dp. V is constant. I'll pull it out of the integral. So I've got minus v, just looked up, times P2 minus P1. Okay, so the integral becomes easy. Don't forget that pesky minus sign. So I'm going to write down that this is not a formula. It's something that you can derive from the fundamental relationship. The work, W dot over M dot of the reversible pump is V at the inlet, V1 times P1 minus P2. Okay. You see you're going to get a negative number here since P1 is a lower number than P2. That's what you expect. W rev is a negative number. All right. So SI units, V1 is going to be in cubic meters per kilogram. And so let's see, delta P is going to be in kPa, kilonewtons per square meter. And so if you use those units, cubic meters per kilogram and kPa, you're going to get W rev in kilojoules per kilogram if you're in SI. If you're in English, this is important. V1 is in cubic feet per pound mass. Your delta P term needs to be in pounds force per square foot, not pounds force per square inch. So you got to do that. Change your pressure increase to pounds per square foot. So that's going to, and what are the units of W reversible going to be in English? It's going to be in foot-pounds force per pound mass. That is important in English. My whole career was, nearly all of my career, except for 1 year, was totally in the English system. So I've got to remember, if I need W reversible pump in BTUs per pound, which is what I always do, I've got to use that identity in English, 770 foot-pounds force equals 1 BTU, because I need my work reversible in BTUs per pound. That is a common thing that undergraduates overlook. Okay, step 3. So what are we driving at? Figure out how much power does it take to drive the pump. All right. Well, we've got now W reversible. We somehow found pump efficiency. We found it, let's say, on a pump curve, or we were given pump efficiency. Okay. So we're going to calculate W actual once we've got these two values. Eta pump, dimensionless. W reversible pump is going to be kilojoules per kilogram or BTUs per pound mass. We've got little W actual. Okay, step 4. We were given M dot. So we imagine that we typically always know the mass flow. Okay. And so we will solve. So remember, little w is W dot over M dot. We're looking for W dot. So W dot actual is going to be equal to, gosh, look at this. My dot needs to be over top of the M, not over the W, for heaven's sakes. W dot actual is M dot times W actual. Gosh, again, how embarrassing that dot is misplaced. But do you see that? I'm not going to fix that right now. But do you see that that's what you're driving for? W dot, the power, the kilowatts, the BTUs per hour. So the output power is going to be less than 0 since power is required to drive the pump. All right, so that gets you well on your way. So that's step 4, and we've checked off the power required to drive the pump. Some more notes on how do we determine the actual outlet enthalpy? I want to give you those because it turns out that for a pump in a power plant, you've got to pump your water up into a boiler, also known as a steam generator. And so when you look ahead and you're planning an engineering analysis on a steam generator, you've got to know the inlet enthalpy of the steam generator. So therefore, you need H2 actual. You need H2. That's why I want to show you how to get that. Okay, what we're going to do is we're going to use the first law, dividing it, the first law for this open system steady state steady flow by M dot. And I'm not going to drag you through. So do you see what I've done here is I've written out the first law, but I've divided everything by M dot. I'm striking out kinetic and potential energy changes for the pump. Our pump is fully insulated, so I'm striking out Q in. Little W actual, I've got a number for that. H1, I looked that up. in my temperature table. So I can solve numerically for H2 actual using the first law written across the pump. Okay, so that's an important, that's a high value piece of advice for you, because that we're looking ahead towards putting all of these little open system components together to create a system operating in a cycle. So that's my notes on. Here's how you determine H2 actual. You use the first law. Now, even though I've worked through some details with you, sort of given you some verbal advice, it's always a little more comforting to see some example problems where the numbers are worked out. And in my pump kit, if you go to example problems, open systems playlist, you click on pump calcs. I'm giving you two example problems, one for a pump power calculation in SI, and one example for a pump power calculation in English. And that'll help, I hope, help you work through the details of the numbers and dealing with the numbers. Okay, couple of slides with a couple of blunders. Thank goodness I was able to go into the edit mode and fix one of those slides. I'll go back and fix that other slide here in just a minute. It's my hope that not only did I help you get, what did we accomplish there? Let's see. We introduced a new idea called W reversible for an open system. W dot over M dot is minus the integral of VDP. That's covered in your textbook. I wanted to drive that home. We defined pump efficiency. My claim is that you can figure that out in your head. You don't need a formula to figure out pump efficiency. And then finally, I tried to give you some tips on how would you go through a very typical pump calculation, because it's so common to do that both in the rest of this class, through the next 2 years of your undergraduate experience. You're going to be working with pumps in your fluid mechanics class. And you may be working with some pumps in your heat transfer class as well. So I hope that helps. And we've got one more efficiency to do, and that's going to be nozzle efficiency associated with open systems.